So let's work on this problem. Now, excuse me. Remember, we've been working on writing the internal shear force and bending moment as functions. This one is different than the ones we've worked previously. What looks different about this one? Well, if you look at the loading, this loading in this section here, it's not continuous across the whole structure. So what that means is we'll have to write one set of equations that's valid over this load, which if we're going from left to right will be from 0 to 12 feet. And then we'll write a second set of equations that are valid from 12 to 20. That will tell us how shear moment vary there. So we'll have to make, we'll use the method of sections, but we'll have to use it twice. In both cases, we'll have to decide which side of the free body to use. So I'm going to draw a line here, and this will be the section that I'm going to cut somewhere between 0 and 12. And do you want to work the left side or the right side? Well, let's talk about the left side. What's the advantage of the left side? Well, the load's pretty simple, right? But the disadvantage would be I'd have to find the reactions. If I look at the right-hand side, no reactions, but the description of this load might be a little challenging. Now, when you go to do the other section from 12 to 20 out here, I need to look at the whole left side, right? Again, I need reactions and describe this load, or just this little right-hand piece. And I think you can see that's probably going to be a lot easier to do. So I think what I'll do is do both. So in section 0 to 12, I'll work the left side. And then from 12 to 20, I'll work the right side. So since I've made that decision to go to the left here and then to the right here, I'm going to need to find my reactions at A. So I'll come over here first and we'll draw a free body diagram of the structure. And I will replace, well, first let me write what I do know. I know that out here on the end, I have a load of 20 kips. And I'm going to replace this concentrated equivalent load, this distributed load with the concentrated equivalent. So first I want the area under this curve. What's a rectangle? So that's going to be the base, which is 12, times the height, which is 4. So 4 times 12 is 48. So I know the force is 48 kips. And it's going to act in the centroid of this area. Well, again, the rectangle is easy. It's just half the distance. So there will be my equivalent force. It's 48 kips. And from the left edge, that would be 6 feet, half the distance. The remaining distance would be 14 feet. Now, on the left edge, I'm going to assume positive shear force and positive bending moment. And we'll find those two things. That's not too hard. I can just use my statics equation. So first we'll sum forces about where? Where would be a good place to sum moments in this structure? Probably right there. Your shear force acts through that point, so it won't create any moment. So I'll have my unknown moment in terms of things that I know. So I'm going to sum moments at A and make sure it's in equilibrium. There's my statement. And now with right-hand rule, yeah?
You're not solving for reactions first?
I am. So I do the free body diagram of the whole thing, and these are my reactions. Shear force and bending moment at A. I guess I should have put subscript these A. So I'm not cutting that in some arbitrary distance here. That is at A. So with right-hand rule, this moment is negative. The moment caused by the 48 kip force about A is what? Positive or negative? Negative. So the force is 48 kips, and the distance is 6 feet. And what about the 20 kip force out here at the end? About A, positive or negative? Negative. And the force is 20, and the distance is 20 feet. So I should be able to solve for the moment at A. It looks like it's going to be negative. Somebody's going to have to help me with that. What's that?
688.
What is it?
688.
688. Anybody else get 688? Just to be sure. I know this is 400. I don't know what that is off the top of my head.
288.
488? No, 688.
688.
688. And that will be kip feet. And it's negative. Does it make sense that you'd have a negative bending moment here at the reaction? I think so. How's this thing going to bend? It's going to kind of bend probably something like that. All right? And you can see that whole side looks like it's concave down. So probably this whole beam is going to have negative moment in it. Now I can get the shear. All we have to do is sum forces in the y direction and make sure that's in equilibrium. So there's our statement. And now I'm going to assume up is positive. So let's go add up all of our forces. So that shear force is up, so that's positive. My 48 kip force is down, so that's negative. And the 20 kip is down, that's negative. So it looks like the shear at A is 68. So we have a positive bending moment, a negative bending moment and a positive shear force at A. That was just the reaction. So now I'm going to go back and we're going to look at the variation of moment over the first 12 feet. So that would be, the range will go from 0 to 12. And we've already talked about when we make our arbitrary cut in that range, we're going to look at the left-hand side. So let me draw the free body diagram for that left-hand side. So there's the structure. We're cutting at an arbitrary distance x. We still have the distributed load applied. And that has a value of 4 kips per foot. Now, what are our reactions here? Well, we have a positive shear force acting up equal to 68 kips. And we have a negative bending moment, which we found to be 688 kip feet. So those are the things that we know at A. And now we're going to find at our arbitrary cut, I'm going to assume there's my positive shear force, there's my positive bending moment. So only two things I don't know, shear and moment. And you'll notice that all this stuff is going to be a function of x because we're cutting at an arbitrary distance x. So I know I'm going to have an equivalent force and a distance from the cut. So what is the force equal to? What's the area of this curve, and what's this curve? It's a rectangle. What's the area of a rectangle? Base times height. Base is x, height is 4. So my force is just going to be 4x. And the distance from the cut to the centroid of the rectangle is always what? Half the distance. And the distance is x. So half of that will be x over 2. So there's all the pieces. Now I just need to sum moments and forces to find that. So we'll let me just make a little line here to kind of break that off from the rest. So then we'll come over here and we'll sum moments now at this cut and make sure it's in equilibrium. So again, I'm using right-hand rule. So starting here, what kind of moment is this with right-hand rule? Positive or negative? Positive. So that'll be moment. Now, does this shear force create any moment about the cut? No. Now, this force, the way I've drawn it here, F, is that going to create positive or negative moment about the cut? Positive. So the force is 4x, times the distance of x over 2. Then I get here on the end, and I've got this 68 kip force that's acting up. What kind of moment does it create about the cut? Negative. So that'll be a force of 68 times the distance of x. And then finally I have this moment, and using right-hand rule, that's what I'm using for my sign convention. What kind of moment is this? Positive or negative? Positive. So I'll just say plus 688, and that has kip feet. So now I'll go back and solve for my moment. It's going to be a function of x. And positive, I just put everything on the other side of the equation. So I got 4x times x over 2, that's 2x squared, that's minus plus 68x minus 688. And all those terms will have the units of kip feet. So there's my moment. Can I check this right now and get any kind of feedback? Well, I do know the moments. Do I know the moments somewhere between 0 and 12? I don't know it out here at 12, but I do know it at 0. In fact, I do know that the moment at x equals 0 should be negative 688 kip feet. Now, when I plug in x equals 0 here, 0, 0, what do I get? So that works. 688 works. So far that works. So now let's find the shear. So I will now sum forces in the y direction. There's my statement. So let's do that. Looking at my free body diagram, with up being positive, this shear force is down, so that's negative. My concentrated equivalent force is down, so that's negative. It's equal to 4x. And I got this 68 force acting up, so that's positive, and then it'll be plus 68. So I can solve for my shear as a function of x. And what do I get? I get minus 4x plus 68, and that should all have the units of kips. Do I know the shear anywhere from 0 to 12?
0.
Yeah, at my reaction. So I'm hoping that my equation tells me that the shear at x equals 0 should be what? 68. So plug in x equals 0, and look what you get. You get 68. That's cool. What else can you check now? We haven't derived it yet, but we've kind of empirically found that we think the derivative of the moment is equal to the what? The shear. If you take the derivative of this polynomial, what do you get? You get minus 4x plus 68. So that's also valid. So there's a couple of checks right there to let you know that you're probably doing okay right now. Any questions about that? That's probably the hardest part of this particular problem. So to finish it up, we want to do it somewhere here. So this is going to be a value of between 12 and 20. So we've already talked about this a little bit, so I'm going to cut it here between 12 and 20. We've already decided to look at the right-hand side. So I'm going to draw that. So there's the right-hand side of my structure with the load 20 applied. Now remember, we're measuring x from the left side, so x will bring us up to the cut. Right? So what is the remaining piece of this segment? Yeah, the total distance is 20, so this piece should be 20 minus x. And you can see for any x value, if you add these two segment links together, what do you get? You get 20. So that's good. So now I'm going to assume at my cut surface positive shear force and positive bending moment. and I can apply my two equations of equilibrium to this free body diagram, and I should get those results. So let's do that real quick. So I'm going to sum moments at the cut. Make sure they're in equilibrium. So there's my statement. So what are that? So with right-hand rule, what kind of moment is this? Positive or negative? Negative. And this 20 kip force about the cut is creating what kind of moment? Negative. Right? And the force is 20. And what's the distance? This distance. 20 minus x. So solve for the moment as a function of x, and you can either leave it in this form or you can expand it however you want to do it. I'll just leave it in that form. So I'll get minus 20 times 20 minus x, and that'll have units of kip feet. So there's my moment expression there. Now, do I know the moment anywhere out here between 12 and 20? What's the moment at the free end? 0. Right? It's free. And there's no applied moment there, so that means that at x equal 20, what should my moment be equal to? 0. Does my equation there say it's 0? It does. So that works. I'm going to have to squeeze this one in, but I think we can fit it. So the last one would be to sum the forces in the y direction and set equal to 0. So there's my equilibrium statement. And what do I get? Well, I'm assuming up is positive, so my shear is up, so that's positive. And this 20 is down, so that's negative. That's pretty easy. That just says the shear is equal to 20. So it looks like the shear is constant in that section and equal to 20. Now, does it make sense that the shear is equal to 20 right there? If I were to take that little section and draw a little tiny free body diagram. So here's my little teeny tiny free body diagram. In fact, it's so small, it's only delta x wide. And on this side, I have my 20 kip force. And at the cut, I have what? Positive shear. So just look at how those two forces balance. Do they balance? So it looks like the shear is equal to 20. That's exactly what the equation says. One more check we can do. Is the derivative of our moment with respect to x equal to the shear? The answer is yes. So we do get also the check that the derivative is equal to the shear, and that's true. If you're like me, if you're just crazy and you got to check one more thing to make sure, what else do we know? Is there some way to relate this moment to this moment? Do they share one point in common? Yeah, they both have a value at 12. So you could put in 12 here, and you could put in 12 here, and those should be equal. That's a little harder to do off the top of your head, but look at the shear. What about the shear at 12? Well, that's 48, negative 48 plus 68. That's positive 20. And what's the shear given by this one at 12? 20. So it matches. The only time that wouldn't match is if there was an applied force right at that common point. So I'm showing you all these different things because I want you to have the ability that when you write these equations, get some feedback that they're going in the right direction. Give you some confidence that you've got them right. So any questions about this one?